if I square this, I'm just making gas B gas 2 because I wanted it down there. But if I square this, so what can we say about their relative masses then? Who's bigger, gas A or gas B? Who's heavier? I mean, who's got the bigger mass?
Okay.
Well, think about this. They're at the same temperature. Gas B diffused faster.
Okay.
So A is going to be bigger because a lighter gas is going to move quicker through the tube. A heavier gas is going to move slower if they're at the same temperature, and they are. But how much bigger is gas A? Well, 4 times as big, 4 times the mass, because it gets squared. So lighter gases diffuse faster than heavier gases, as long as they're at the same temperature.
Where's B and where's A?
Ice made gas B number 2 and gas A number 1. So if it's diffusing twice as big, its speed is going to be twice as big as A.
Okay.
What if I said it's 3 times as much? How much bigger is A now? 9. So gas A is 9 times as heavy as gas B. Why don't we try number 2 in that little packet that I handed out to you. This is from 2003. So you've got a rigid 5-liter cylinder that contains nitrogen and oxygen gas. Calculate the total pressure of nitrogen and oxygen, okay? So we've got a cylinder, it's rigid, so it's not going to change shape. It's got nitrogen and oxygen. Are these two gases reacting? Is there any reaction going on in here? Okay, good. Because if there's a reaction going on, then we approach the problem differently. But these two gases are acting independently of each other. They're not doing anything. So the total pressure in here should be the sum of the individual pressures. We've got 24.5 grams of nitrogen and 28 grams of oxygen. So 24.5 grams of nitrogen and that's going to give me 28 grams of nitrogen is 1 mole, and I've got 28 grams of oxygen and 32 grams of oxygen gives me 1 mole of oxygen.
It's 0.875 moles of nitrogen.
Thank you.
And 0.875 moles of oxygen.
The same?
Mm-hmm.
Okay. So you can probably tell that's by design. The number of moles are equal. So that means the pressure exerted by the nitrogen is equal to the pressure exerted by the oxygen, because they have the same number of moles. They don't give us the total pressure. we can calculate the pressure using PV equals nRT. Now you wouldn't do this separately for each of these, because that would take, well actually we could just do it for one of them because the pressure will be the same, because of the ideal gas equation. So P is equal to nRT over V. The pressure is going to be 0.875 moles times, do they want it in a certain pressure? ATMs, so we'll use the 0.0821. Times our temperature, which is 298. Over our volume, 5 liters. And I get 4.28 atmospheres. So if one of these is 4.28 atmospheres, then because their moles are equal, the other one will be as well. And the total pressure will be 8.56 ATMs. Okay, it says for B, the temperature is decreased. Can I erase this? So right now, what is the ratio of nitrogen to oxygen in our container? 50-50, right? They have the same number of moles. This is at 298. If I decrease, Kelvin, if I decrease the temperature, will that affect the amount of nitrogen and oxygen in there? No. So the ratio will still stay the same. Now, remember I said there's no reaction going on. It'd be a whole other story if there was some reaction, like if they had, I don't know, hydrogen gas and oxygen gas in there, and they're looking at some sort of equilibrium reaction. They're not. The nitrogen and the oxygen, the ratio will stay the same. If you lower the temperature, it just means they can be moving slower. Okay? So if they're moving slower, they will hit the container with less force, your pressure will be less. So all you gotta do is recalculate PV equals nRT, but this time, instead of using 298, you're going to use 280. And that will give you the total pressure. And I'll just do that real quick. At 4.02. So instead of being 4.28, the pressure dropped to 4.02. And it would be the same for the oxygen. Okay, if the cylinder develops a pin-size hole leak, some of the gas escapes. Would the ratio of N2 and O2 increase, decrease, or remain the same? Now it gets interesting. So there's a hole in the bucket, dear Liza. You decrease the temperature, the ratio stayed the same. But now, are the two gas molecules going to diffuse at the same rate? Or is one going to move faster than the other one out the hole? Now, what did we just get done talking about when we had Graham's law up here? who diffuses faster, a heavier gas or a lighter gas?
Lighter.
The lighter gas. So which one's lighter, nitrogen or oxygen?
Nitrogen.
Nitrogen. So the nitrogen gas will leave the container at a faster rate than the oxygen. So that means if the nitrogen's leaving at a faster rate, the partial pressure of nitrogen will go down at a faster rate. So, did they ask us to calculate it or just?
No,
Okay, so it's going to the ratio of the moles. Well, the ratio of moles of N2 over O2, the ratio will get smaller, right? Because, and this is where you gotta be careful, if the number on top gets smaller, that means the ratio is getting smaller. Okay? Oh, now they're doing a reaction. A different rigid container contains 0.176 moles of nitrogen monoxide. A 0.176 sample of oxygen is added to the cylinder where a reaction occurs to produce NO2. So we've got nitrogen monoxide, 0.176 moles of it. And we're gonna add an equal amount of oxygen. And so the nitrogen monoxide and the oxygen are going to react to produce nitrogen dioxide. To balance it off, we're going to need 2 there and 2 there, and we're balanced, right? So calculate the total pressure after the reaction is complete. So they do not give us a KP. So we have to assume that the reaction goes to completion. Just making sure I'm not missing anything here. Okay, so I don't see it, if they gave us a KP, okay, if they gave us a KP, we'd have to do an ice table and do our concentrations and shift and find the equilibrium concentrations based off of we have to do that if they gave us a K value for this reaction. They did not give us a K value. So if there's no K value, then we're assuming that the reaction is going to completion, and therefore it's just a limiting reactant problem, meaning which one are we going to run out of first? Are we going to run out of nitrogen monoxide first or oxygen first? Which will be the limiting reactant? Well, we can kind of already tell. They gave us the same number of moles. The nitrogen monoxide will be used up as twice as fast as the oxygen. Right? So before my reaction, I have this many moles of each. These will be used up faster. So after the reaction is done, all of it is gone, how much oxygen will be left? Half as much. How much of the nitrogen dioxide will be produced? 0.176 moles, because the amount of this should be equal to the amount of that when we're all done. If you don't believe me, work out the stoichiometry, which you can always do, 176 moles, 2 moles of NO will give me 2 moles of NO2. So, so that's the number of moles of those gases when we're done. Now calculate the total pressure. They didn't ask for the partial pressure, so all of this guy is gone. See you later, alligator. Some of the oxygen disappeared.